Did you know, when the sun is furious, it emits solar flares that can disrupt the functionality of our satellites or anything around it? Yes, solar flares. In this video, I'll explain the sun's mysteries, its core structure, and how it emits horrifying solar flares. Stay tuned till the end so you don't miss any exciting points. Let's dive in. First, let's see what the sun's solar fury is. Solar fury refers to the intense and often violent solar activity emitting from the sun through solar flares, coronal mass injunctions, and solar wind. It can significantly disrupt the functionality of the solar system, especially Earth. Due to the intense flares, components in space related to the Earth, such as satellites, power grids, and various technologies, can be disrupted. Solar fury occurs due to the sun's magnetic field, which undergoes changes and fluctuations due to the movement of the charged particles within the sun. When these magnetic fields are twisted, they release immense energy as radiation. Did you know that in the past, there were many times when the sun's solar fury came into being and many humans living on the Earth were affected by it? Yes, it's not only something that occurs in science fiction movies, instead, it's the reality. Before going into other essential details about solar fury, let's understand the sun's structure. The scientists observed an immensely dense and hot region extending from the center to about 20 to 25% of the sun's radius. Its main point is the powerhouse where the nuclear fusion takes place. It produces the energy that powers the sun. In this extreme environment, temperatures are around 15 million degrees Celsius and pressures exceed 250 billion atmospheres. These conditions are so intense that they allow hydrogen nuclei, protons, to overcome their natural repulsive forces and fuse. In the sun, the primary process is the proton-proton chain reaction. This nuclear fusion generates enormous energy through gamma-ray photons, eventually escaping the sun to provide the heat and light we receive on Earth. Now, here comes the concept of radiative and convective zones. In this layer, the energy produced at its main point travels in the outer direction with the help of radiation. The photons are then generated by nuclear fission and absorbed into the radiative zone by the plasma. This process is prolonged, with photons taking millions of years to traverse this layer due to the high density. As energy moves outward through the radiative zone, the temperature decreases. Then, the convective zone starts from the outer side of the sun's radiative zone and extends towards the sun's surface, photosphere. In this layer, the temperature drops to about 2 million degrees Celsius, making the plasma less efficient at radiative transfer. Instead, convection transfers energy. Hot plasma rises towards the surface. Then it cools as it loses power, sinks back down to be reheated, and rises again. It creates a dynamic environment responsible for the granular appearance of the sun's surface, known as its granulation. Moreover, the photosphere is the sun's visible surface layer. It is approximately 500 kilometers thick and emits most of the sun's visible light. With temperatures ranging from 4,500 to 6,000 degrees Celsius, it features sunspots caused by magnetic activity. Now, it's time to explore some solar phenomena. First are the sunspots. They are the dark spots on the surface of the sun. These sunspots are cooler, so their appearance is darker than that of the other areas of the sun. Well, you'd be wondering how sunspots are caused. So, due to magnetic activity, these sunspots exist on the sun's surface. The lines related to the magnetic field near sunspots are concentrated and twisted. This inhibits the convection currents that bring hot plasma from the sun's interior to the surface, causing the region to become cooler. Sunspots usually appear in pairs or groups with opposite magnetic polarity. They are indicators of solar activity. They are closely associated with solar phenomena such as solar flares and coronal mass ejections. The number of sunspots on the sun's surface fluctuates over an approximately 11-year cycle known as the solar cycle. During the solar maximum, sunspots numbers are high, indicating increased solar activity. On the other hand, when the solar minimum is reached, the sunspots numbers decrease. This means reduced solar activity. Now, what about solar flares? So, they are intense bursts of radiation coming from the sun's atmosphere. They occur when magnetic energy stored in the sun's atmosphere is suddenly released. This energy release accelerates charged particles, primarily electrons. These particles then collide with the dense plasma of the sun's lower atmosphere, where they get heated and cause the emission of X-rays and gamma rays. The primary cause of solar flares is the reconnection of magnetic field lines near sunspots. As magnetic fields, they store energy. The stored energy is released as a solar flare when these fields suddenly reconnect. Solar flares are also classified based on their X-ray brightness in the wavelength. The classification system includes A, B, C, M, and X, with each letter representing a 10-fold increase in energy output. Well, the X-class flares are the most powerful. They can have significant effects on Earth. Do you know about the coronal mass ejections? These are massive outbursts of solar wind and magnetic field rising above the solar corona or being released into space. CMEs are often associated with large solar flares and complex sunspot groups. CMEs occur when the sun's magnetic field lines reconnect explosively. The energy in the magnetic field propels plasma away from the sun. Unlike solar flares, which are localized bursts of radiation, CMEs involve a significant mass ejection. They can have long-lasting effects on the solar system, and space weather suffers greatly. When a CME hits Earth, it can interact with the magnetosphere. Then, it causes dangerous storms for the Earth. These storms can create a current in the power lines, which can cause the loss of power. They can also affect satellite operations, GPS systems, communication networks, and electronic components. One of the most well-known effects of CMEs is the enhancement of auroras. When the CME and the Earth's magnetic field interact, charged particles are created. These particles then develop lights. However, these interactions can also threaten polar routes, disrupting communications. Before discussing the historical detail of solar storms, let's subscribe to the channel. This way, you can uncover the mysteries of the cosmic world and thrive in space. The Carrington Event of 1859 was the most powerful solar storm recorded in modern history. It started with a colossal solar flare, an intense burst of radiation from the sun's surface. It was swiftly converted into coronal mass ejection, which released a burst of solar wind and magnetic fields into space. Due to this, telegraph systems around the world experienced severe disruptions. Sparks flew from telegraph equipment, causing fires and electrical shocks to telegraph operators. Remarkably, some telegraph systems continue to operate even after being disconnected from their power sources. Well, that's an interesting factor to note. The Carrington Event produced stunning auroras visible at unusually low altitudes. Auroras were reported as far south as the Caribbean and Hawaii, and people in the northeastern part of the United States reported that they could read newspapers by the light of the auroras. Well, the Carrington Event was groundbreaking. It was the first time a solar flare was observed with significant geomagnetic effects on Earth. Moreover, in May 1921, a powerful geomagnetic storm disrupted telegraph and telephone systems across the United States. This event demonstrated the vulnerability of early electrical and communication systems to solar activity. In March 1989, another powerful coronal mass ejection caused a geomagnetic storm that affected power grids and communication systems. The Hydro-Quebec power grid in Canada collapsed, which caused many electricity issues. This event highlighted the potential impact of solar storms on modern infrastructure and the need for improved space weather forecasting. Another storm, the Halloween storm, comprised of a series of powerful solar flares and CMEs. These storms caused intense geomagnetic disturbances that disrupted satellite communications, GPS signals, and power grids. The storms also produced vivid auroras visible at unusually low altitudes, including parts of Texas and Florida. Have you ever wondered what the future of the sun will be in the upcoming years? Like all stars, the sun follows a predictable life cycle shaped by its mass and composition. Currently, the sun fuses hydrogen and helium at its core in its main sequence phase. Over the next 5 billion years, the sun will continue to burn hydrogen at its core. It gradually transforms into a red giant as its hydrogen fuel diminishes. During this phase, the cores will contract and heat up while the outer layers expand outwards, causing the sun to swell to many times its current size. Following the red giant phase, the sun's core burns helium, where helium atoms fuse to form carbon through the triple alpha process. This phase is relatively short compared to the main sequence, which will last a few 100 million years. The evolving sun will affect the other planets in space or the solar system. The expanding sun will likely destroy Mercury, Venus, and Earth during the red giant phase. However, some models suggest that the Earth might survive if the sun loses sufficient mass through stellar winds. The intense heat and radiation from the red giant sun will alter the environments of these planets. Moons and smaller bodies which are orbiting these planets will also be affected. Let's recall what we've learned in this video so far. Solar flares are sudden bursts of radiation, and CMEs are massive expulsions of plasma and magnetic fields. They represent the most potent manifestations of the Sun's solar fury. Solar flares release intense bursts of energy across the electromagnetic spectrum, which poses risks to satellites, communication systems, and even astronauts in space. CMEs can also create intense solar storms that are hazardous for the Earth. Understanding and predicting solar fury is crucial for protecting modern technology and infrastructure, which are increasingly dependent on reliable satellite communications, GPS navigation, and stable power grids. Moreover, studying the Sun's solar fury offers insights into the behaviour of other stars throughout the universe. Space is warped with amazing mysteries, and every planet in space, like the Sun, has its own story. That's why we should always seek knowledge to appreciate the mysteries that lie in nature. That's all for today. Share your thoughts and questions in the comments section.